A certain basketball player scores 60% of the free throw shots she attempts. During a particular game, she gets 6 free throws. What assumptions must be made in order to regard this as a sequence of Bernoulli trials? First off, what is a Bernoulli trial? A Bernoulli trial is an experiment with just two outcomes. Those two outcomes can be called success and failure. In this example, the outcome, which is the success, is scoring on a free throw shot, and the outcome that is a failure is missing on a free throw shot. Sometimes the numbers 1 and 0 are used to represent the outcomes success and failure respectively. So we could call this number 1 and this 0. And if x is the random variable that takes on these values, success or failure, or 1 and 0, then the probability that x equals 1, that is a success, is denoted by the letter small p. In this example, probability of a success is 60%, which is 0.6. That's the probability of scoring from a free throw shot. The probability of failure, which we can call 0, is 1 minus p. See, there are only two outcomes. So the probabilities associated with these two outcomes must sum to 1. So this probability must be 1 minus p. That's 1 minus 0.6, which is 0.4. What is a sequence of Bernoulli trials? A sequence of Bernoulli trials is a finite number of identical Bernoulli trials. In this example, we are talking about a sequence of free throw shot attempts. If we want a sequence of Bernoulli trials which are identical, then the trials have to be independent of each other. So, if they're identical, then this probability mustn't change. The probability of a successful free throw shot, that is the probability of scoring from a free throw shot, must always remain 0.6. It should not change from throw to throw. So the trials have to be independent. Independent means that the probability remains the same for each throw. In particular, this means that if she scores with a particular throw, it has no effect on the probability of her scoring in the next throw. The probability is still 0.6. Even if she scores 10 times in a row, the probability of scoring on the 11th throw should be 0.6. That's what's meant by independent events, independent trials. Based on such assumptions, find correct to 3 decimal places the probability that 1. She scores on exactly 4 of the 6 shots. What we are dealing with here is 6 free throw shot attempts. So that's denoted by the letter n. So we have n equals 6 Bernoulli trials. The probability of success, that is the probability she scores on any particular shot out of the 6 shots, is 0.6. The probability that she misses, 1 minus p, sometimes denoted by the letter q, is the probability is 1 minus 0.6, which is 0.4. If we let x be the random variable representing the number of scores that she gets out of 6 throws, then x follows a binomial distribution with parameters n equals 6 and p, the probability of success, is 0.6. The probability density function for the binomial distribution is nc little x p to the power of little x times 1 minus p to the power of n minus x. I've explained this in detail in other videos. So x in this example is the number of scores out of 6 attempts. So x takes on values ranging from 0 to 6. So x takes on values 0, 1, 2, 3 up as far as 6. She can get no scores, exactly 1 score, exactly 2 scores, all the way up to exactly 6 scores. So in this question, we just plug in 4 for little x. So the probability that x equals 4 is nc4, n is 6. So we just plug 6 in for n. So we have 6c4, p is 0.6. Plug 0.6 in for p to the power of x, which is 4. 1 minus p is 0.4. And we put that to the power of n minus x, where n minus x is 6 minus 4, which is 2. So we get this here. 6c4 can also be written like this. It's the number of ways of choosing 4 objects from 6. Here it's the number of ways that she can score exactly 4 times out of 6 attempts. 6c4 is the number of ways that can happen. You know, she could score on the first 4 throws with probability 0.6 to the power of 4 because they're independent events. We multiply the probabilities together, but then she'd have to miss on the last 2 throws. So we'd have the probability of missing, which is 0.4 times itself. But that's not the only way that can happen, of course. 6c4 gives all the different ways it can happen. So that's a kind of a brief explanation of this, which I go into in more detail in other videos. But anyway, you can run this through your calculator, and to 3 decimal places you get 0.311. What is the probability that she scores for the second time on the 5th shot? So she must score on the 5th shot. So the probability that she scores on the 5th shot is 0.6. Well, the probability that she scores on any shot is 0.6. But that's the 5th shot. So that event is independent of how she scored on the first 4 throws. In the first 4 throws, we just want her to score exactly once, because we want her second score to happen on the 5th throw. So we just want the probability of scoring once in 4 throws among 4 throws. So here we have a binomial distribution. But in this binomial distribution, n equals 4. P, the probability of a success, is 0.6 as before. 1 minus p then is also 0.4 as we've seen already. So here we want the probability that x equals 1. So we want her to score once among 4 throws. So we have ncx, so n is 4, so we have 4c1, p to the power of x, 0.6 to the power of 1, and then 1 minus p, which is 0.4 to the power of 3. This is n minus x, 4 minus 1. These two numbers add up to 4. 1 and 3 is 4. So this is the probability that she scores just once out of 4 throws. So it's just a binomial distribution with n equals 4, and the other parameters are the same. So we can think of this question as defining 2 events: getting a score of 1 among the first 4 throws, just scoring once, and scoring on the 5th throw. So this is just 1 throw. So the probability of scoring on 1 throw is 0.6. These are independent events, these two. So what happens here does not affect the probability of her scoring on the 5th throw. So when we have independent events, we multiply the probabilities together. If we look at this quantity here, we get 0.1536. Notice that when we multiply by 0.6, we get this smaller probability. 0.092 is less than 0.1536. That is exactly what we expect. 0.1536 will be the answer if we're not interested in the 5th throw, if the 5th throw can be any outcome. But because we're forcing the 5th throw to be a score, we decrease the probability. So it makes sense to multiply to get a smaller probability. Of course, adding these would make no sense whatsoever. If we add these numbers, we would get a larger probability.